So I promised there was going to be a little bit of a video on radicals. So I just want to go over the sheet. This should help you out with your homework. Feel free to pause it, rewind. I'm going to tell you to pause at certain points and try the problem just for some practice. So right here we have the definitions. A radical expression is an expression containing a radical. Pretty self-explanatory. Anything that has one of these radicals, 2 times the square root of 7x, or the square root of the quantity x minus 5, or the cubed root of 5x squared. The thing underneath the radical symbol, the 7x in this case, the x minus 5 or the 5x squared, is called a radicand. And the index is the little number in the crook of the radical symbol. It tells you to take the root. It tells you the root to take. So when you have the cubed root over here, I'm going to circle that in blue quickly. You have a radicand of 3. When you have the square root, there is no radicand that you can see. However, it's implied that the radicand is 2. And a simplified radical is all perfect factors removed from the radicand. So what you have here is, I want you to remember that x times x equals x squared. And that the square root of x squared is going to be x. Because what this radical is telling us, or it's asking us to do, is what number times itself 2 times equals x squared. Well, that's x. Over here on the right, it's asking for the cubed root of x squared and saying what number times itself 3 times gives us x squared. And that's not something we can do to create a perfect factor because the 3 is greater than the 2. So if you actually look at this, well, let's look at the cube first. So down here on the next line, we have x times x times x equals x cubed. So if we want to know what is the square root of x cubed, using the property of radicals, we know that x squared times x equals x cubed. So we can break this up, and then we know that this equals the square root of x squared times the square root of x. Since we established in the above point that x times itself gives us x squared, we can simplify this x here in this pinkish color to x, and the square root of x stays as a square root of x. But if we're trying to find the cubed root of x cubed, notice the radicand has a 3 here. We're trying to find out what times itself 3 times is going to give us x cubed. Well, we know from here that that's x times x times x, because you're adding the exponents. So x to the first times x to the first times x to the first equals x to the 1 plus 1 plus 1, or x cubed. And then down here is just building on that. So we have x times x times x times x equals x to the 4th. The square root of x to the 4th is saying what times itself 4 times is going to give us, or what times itself 2 times is going to give us x to the 4th. We know that's x squared times x squared because, again, we're adding the exponent. So x squared times x squared. We can break this up into the radicals. It's going to be x squared, the square root of x squared, times the square root of x squared. These simplify to x times x, which then you combine and gives us x squared. Now, one shortcut, the cubed root of x to the 4th is going to be similar. So we want to break it down to the cubed root of x cubed times x. Separate them. X cubed times x cubed times the cubed root of x. The cubed root of x cubed is going to be x times the cubed root of x cubed, and that's our final answer. Now, an easy way to do this, let me find my clear the page. I do not see a clear the page. Is to look at your radicand. So on the squares, we know that there is an implied radicand of 2. Or I'm sorry, an index of 2. what you can do is look at this index number and try dividing it into the exponent of each individual term under there. So right here, 2 goes into 2 one time, leaving us with just x to the first. On the second one right here, 2 goes into 3 one whole time with a remainder of 1. And on this one down here, 2 goes into 4 two times, leaving us with x squared. And the same thing holds true for x cubed, or the cubed root. So 3 doesn't go into 2 an even number of times, so we're left with the cubed root of x squared. 3, however, goes into 3, we're here at the blue x, one time, leaving us with just x to the first. And 3 goes into 4 one time with a remainder of 1, leaving us with a perfect x and an x to the first under there. So I'm going to go through these problems now, and I want you to pause the video and give them a try when I ask you to. So look at the square root of 192 and think about that perfect square sheet that I have on the Google Drive. What perfect square factors does 192 break into? Well, if you go into your calculator, you can start dividing 192 divided by 4, divided by 9, divided by 16, by 25. And eventually you'll find out that the square root of 192 equals the square root of 64 times 3. Why do we pick 64? For the same reason that we're doing up here with the variables. It's the largest perfect square that goes into 192. So once we use the property of radicals, we simplify this to the square root of 64 times the square root of 3, and we get a final answer of 8 times the square root of 3. Because the square root of 64 simplifies to 8, it stays times the square root of 3. We then combine it for this final answer here. All right, so now look at x to the 5th. We're looking for the square root of x to the 5th. So I want you to answer yourself now, what is the index for the square root of x to the 5th? And what do you think the answer is? All right, so this is saying what times itself 2 times is going to give us x to the 5th. Well, we know that x to the 5th can simplify down to x to the 4th times x. Notice since we have an index of 2, we're trying to pick an even exponent here. Because we know that 2 divides into 4 2 times. So because of that, we now have x to the square root of x to the 4th times the square root of x, leaving us with x squared times x. And if you use that shortcut, you divide 2 into 5, it goes in 2 whole times, which leads us to, I'm going to highlight this in green. So 2 goes into 5, 2 whole times, with a remainder of 1. So go ahead and give the square root of 24 a try. Pause the video. Think about your perfect squares. What factors does 24 break into? Remember, your perfect squares are 1, 4, 9, 16, 25, etc., etc. And then unpause when you have the answer. All right, so you know the square root of 24 breaks down into the square root of 4 times the square root of 6. Because 4 is a perfect square, you can simplify this 2 times the square root of 6. And then this last one, we have a number on the outside, -5. So just don't think about the -5. Focus on the square root of 300. So go ahead, pause it and see if you can figure out what 300 factors into that has a perfect square. All right, so if you follow along, you'll have the square root of 300 equals the square root of 100 times the square root of 3, which breaks down into 10 times the square root of 3. And one step I did not do here was I forgot to multiply it by the negative 5. So at the end here, you're going to want to multiply negative 5 times 10 root 3. And that's just going to equal negative 50 times the square root of 3. All right, so on the next page up here, we have the multiplication and division properties of radicals. And these problems are a little bit harder. Now we're introducing variables into the equations, whereas back here, we're just focusing on one term underneath the radical. But looking at your multiplication division property of radicals, we can apply this multiplication property all across the board. So when you're looking at the square root of 80p cubed, you can separate that into the square root of 80 times the square root of p cubed. And then treat them just like you were doing before. So the square root of 80 breaks down into the square root of 16 times the square root of 5. And p cubed breaks down into the square root of p squared times the square root of p. Simplify your expressions. So the square root of 16 simplifies to 4. The square root of 5 stays as the square root of 5. The square root of p squared is p, and the square root of p carries down. And then when you're writing your answers, you want to put everything together on one side and everything under the radical under the other side. So you always want your constant, then your variables. So you'll end up with an answer of 4p times the square root of 5p. So go ahead and give this next one a try. You're looking for the square root of 45a to the 5th. So pause the video, try it, and then follow along with the answer. All right, welcome back. So 45a squared breaks down into the square root of 45 times the square root of a squared. 45 breaks down into the square root of 9 times the square root of 5. The square root of a squared, 2 goes into a squared perfectly because we know a times a equals a squared. So you end up with 3 times the square root of 5 times a. Pull everything together. Remember, you want constant, then variable, then radical. So you end up with 3a times the square root of 5. And for this last one, you can apply this with more than one variable. So you have the 3a on the outside. Well, this just breaks down into 3a times the square root of 60 times the square root of a to the 7th times the square root of b to the 10th. So factoring out anything that's even, and you can write this out anytime you want, but you're just trying to divide in if you want to, like you know that the index is 2, you divide 2 into 7 as like a check, or when you feel more comfortable with this. So 60 breaks down into 4 root 15. A to the 7th breaks down to a to the 6th times a. And b to the 10th is even, so the square root of b to the 10th is also going to be even. Then you continue your next step. You have 3a. The square root of 4 simplifies to 2. The square root of 15 stays as the square root of 16. The square root of a to the 6th turns into a cubed. Square root of a stays as the square root of a. And the square root of b to the 10th turns into b to the 5th. Notice these variables here, or these exponents, the 10, the 6, are just getting cut in half when they end up down here. So then rewriting everything and combining like terms, we end up with 6a to the 4th. Don't forget we had an a here and an a here. B to the 5th times the square root of 15a. All right, and for our last 3 problems, this should cover pretty much the last bits of the radicals that you are asking questions about. So for this first problem, we have the square root of the quantity x to the 23rd over 16y to the 16th. So if you remember back on our previous page, looking at the power of radicals here, I'm going to highlight it in red just so you can see. We know that a quantity that's dividing underneath a square root, you can take the square root of each one individually. So let's start with that. So the square root of x to the 23rd over 16y to the 16th equals the square root of x to the 23rd divided by the square root of 16y to the 16th. And once we have that, we can apply our properties of multiplication of radicals to get the square root of x to the 22nd times the square root of x divided by the square root of 16 times the square root of y to the 16th. And since this simplifies pretty straightforward, x to the 22nd, the square root of that simplifies to x to the 11th times the square root of x. The square root of 16 simplifies to 4, and the square root of y to the 16th simplifies to y to the 8th. All right, and then the next one, this is our first cubed root. So when we're taking the cubed root, instead of having an index of 2, like we do here, we now have an index of 3. So if you're using the shortcut, you're looking to divide each of the exponents by 3 and see what remains. So if we're to guess at this, we're going to say, okay, this is going to end up as a to the 3rd. And b, 3 divides into 20 6 times with a remainder of 2. I can't write really well with a mouse. So we're looking for variables that look kind of like that. So the first thing that we want to do is we're going to split it apart. Just like we did with the square root, we can do this to the cube root. So we have the cube root of negative 54 times the cube root of a to the 9th times the cube root of b to the 20th. Going down, we can see that we know that 27 is a perfect cube from our chart, or by knowing that 3 times 3 times 3 is going to be 27. So we're going to take the cube root of negative 27 times the cube root of 2 times the cube root of a to the 9th. The reason we're doing the cube root of a to the 9th, I'll draw that down here, is because a to the 9th equals a cubed times a cubed times a cubed. So because we're looking for the cubed root, we're looking for what times itself 3 times will give us a to the 9th. And the same thing here. We know that b to the 3rd times b to the 3rd times b to the 3rd, or I'm sorry, b to the 6th times b to the 6th times b to the 6th will give us b to the 18th. So notice we now have times b to the cube root of b to the 18th and the cube root of b squared. Simplifying what we can, we have negative 3, because the cube root of negative 27 is going to be negative 3. Remember, negative 3 times itself is going to give us 9. And then 9 times negative 3 is going to give us negative 27. Times the cube root of 2, because we can't break down the 2 any further, times a cubed, times b to the 6th, times the cube root of b squared. And I actually forgot to properly write my answer here. So if we combine our terms where we need them, it's going to be negative 3 a cubed b to the 6th times the cubed root of 2 b squared. To be squared or not to be squared? That is the question. And if you look, when we initially did our quick check, we were looking for a cubed b to the 6th times the cube root of b squared. And right here, that holds true. So the only thing you need to work on is the constant. So go ahead and apply that same principle to the fourth root. Remember, for the fourth root, we're trying to find out what times itself 4 times gives us that number. So pause me, give it a try, and see what you get. And then come back and I will work through the problem with you. All right, welcome back. So we can rewrite this as 4x squared times the fourth root of 81 times the fourth root of x to the 7th times the fourth root of y to the 20th. Because this applies, again, right up here, the fourth root can be broken down just like the square root and the cube root. So we keep the 4x squared with us, and we're trying to find what times itself 4 times gives us 81. Oh, this is something you would just have to practice or do by trial and error. You could do the fourth root of 2, or 2 to the fourth is going to give you 16. Or 2 to the fourth gives you 16. 4 to the fourth gives you 6. I think it's 276, so that's too high. So you go for 3, and you find out that it does equal 3. And then you do the same thing with the x. You're breaking it down into x to the fourth, x to the third, because the fourth root of x to the fourth is going to be x. The fourth root of x to the third isn't an even exponent, or isn't divisible without a remainder. And the fourth root of y to the 20th is going to be y to the 5th, because y to the 5th times y to the 5th times y to the 5th times y to the 5th will give you y to the 20th. Simplify a little bit further. You have 4x squared. The fourth root of 81 is 3. The fourth root of x to the fourth is x. The fourth root of x cubed is x cubed. And the fourth root of y to the 20th is y to the 5th. And then rewrite everything. Remember, you're going to have 4 times 3 is going to give you 12. You have the x squared times x to the fourth here is going to give you x to the 6th. Y to the 5th is there, and then you just have the fourth root of y, or of x cubed. So I hope this helped you with your radicals. If you have any questions, please bring them in on Monday, or Tuesday rather. Your homework for the radicals is worksheet 2, numbers 16 through 20. If you want some extra practice, give 1 to 15 a try. If you have any questions on them, please bring them in. We'll work through them together. I'll answer any questions you have. This should be reflective of what the quiz is going to look like. So enjoy your 4-day weekend, and I will see you all on Tuesday. Ta-ta.